What we're going to do when we start with the gas laws is look at the units and the types of temperature and pressure units we need to look at for gas laws. Okay, does anyone have any idea what STP stands for? Standard temperature and pressure. Yes, good. Okay, so standard temperature and pressure is a condition. It means that if we're at STP, we have a certain temperature and a certain pressure. Okay, but when we use those standard temperature and pressure, we have to have correct units. Okay, so we're going to look at the units for temperature and pressure. All right, so our temperature unit needs to be in kelvins. Do we know how to convert from Celsius to Kelvin?
Plus 273.
No, it's like
273.
Yeah, add 273. Okay, so when we want to go from Celsius to Kelvin, we need to add 273 to whatever temperature in Celsius that we have. All right, if we need to go from Fahrenheit to Celsius, we'll use this equation. It's not used very often. We don't get our temperatures in Fahrenheit very often at all, especially in these scientific problems that we're doing. But if you do, this is your conversion, so you have it. From there, you can just go to from Celsius. So that's our temperature unit. Let's look at our pressure unit now. Okay, our pressure is going to be in what we call atmospheres, or ATM. Okay, ATM is the abbreviation for atmospheres. That's a unit of pressure. Okay, what pressure means in and of itself is it's the amount of force applied over a certain area. Okay, so if you have a little tiny force applied over a big area, what would your pressure be, big or small? If I have a little tiny force applied over a big area, you would have low pressure, yeah, or small pressure. If I have a lot of force concentrated on a little tiny area, my pressure would be high or low? High, okay? So that's kind of how we determine what our pressure would be. There's 4 different types of units that you can identify pressure in, okay? So here's our 4 units that we need to have, be able to convert to and from atmospheres, okay? The first of which is called kilopascals, okay? This kPa is a pressure unit. What this tells us is that 1 atmosphere is 101.325 kilopascals. Okay, so I'm going to put all 4 of these unit conversions up there so you can get them written down, and then I'll talk about them a little bit. Millimeters of mercury, good. Millimeters of Hg, which is mercury. Any idea about when this might be applicable? Close to a thermometer. Something that measures pressure is a barometer. Okay, have you heard the term barometer before? Okay, that's something that measures atmospheric pressure. And what this tells us is that this column of mercury that kind of looks like a thermometer, but it's encased a little differently, that column of mercury is 760 millimeters tall. Okay, and if it gets taller, that means we have more pressure. If it gets shorter, it means we have less pressure. So that's just another way to measure pressure. Torr is our least used of the 4 pressure units. We don't use torr hardly at all. And then PSI we said was about like tire pressure and things like that. Okay, so all of these are equal to 1 atmosphere. And atmospheres is what needs to be our common, most used pressure unit. Okay, so when we want to look at pressure in these gas laws, we're going to put them in atmospheres. Okay, so this is STP precisely, okay? If I say I have a gas at STP, I have a certain set of conditions in which that gas is under. I have a certain temperature and a certain pressure. So if I say a gas is at STP, that means it has a temperature of 0 degrees Celsius or 273 Kelvin, okay? It also has a pressure of 1 atmosphere or 101.325 kilopascals, okay? Kilopascals is the kind of second place pressure unit. That's the second most common. Okay, used scientifically, it's the second most common. So now you need to memorize these conditions so that you understand if I say I have 40 liters of a gas at STP, you know what the pressure is and you know what the temperature is. Okay, that's what STP means. It's a common standard set of conditions. I'm going to look at 3 gas laws. 3 different ones, and then a combination of the 3. So the 3 that we're going to look at, first of which is called Boyles Law, second of which is Charles Law, and the third one is called Gay-Lussac's Law. Boyles Law and Charles Law are the much more common than Gay-Lussac's. And then we're going to look at a combination of the 3 that's cleverly named the Combined Gas Law. Okay, so we're going to look at Boyles, Charles, Gay-Lussac's, and the Combined today. We're going to start with Boyles Law. Boyles Law gives us a relationship between pressure and volume. Okay, so it tells us the pressure and the volume of a gas are inversely related. What this means, this inversely related, it means when one goes up, the other goes down. Okay, if the pressure of a gas gets increased, the volume will get decreased. Okay, or if the volume increases, the pressure decreases. The time that this rule is applicable is when we have constant mass or constant number of particles and when we have constant temperature. If these two things are not constant, that rule does not apply. Okay, so the rule of inversely proportional only applies when we have constant temperature and constant number of particles, okay, or constant mass. Okay, we can relate with this equation. So P here would probably stand for pressure. V would probably stand for volume. And same on the right side. The 1 and the 2, they tell us that this is kind of initial, and this right side is final. Okay, so this is P1, so pressure initial, volume initial equals pressure final times volume final. Okay, or this is like a before and an after, however you want to think about it. Okay, so these are what these subscripts and the actual variables mean. P1 equals pressure of gas initial. It has to be in atmospheres. Volume needs to be in liters. Not milliliters, not gallons, not anything else. It needs to be in liters. So this says 1 liter of gas at STP is compressed to 473 milliliters. What's the final pressure? All right, so we're going to use Boyles Law to figure this out. Go ahead and get it written down if you want to, kind of get your head wrapped around what's happening in this problem, and then we'll start working out the math on it together. All right, so when we start doing these problems, I think it's really helpful to list kind of what we have here in our margins. Okay, make a list of our variables, what we have, what we're given in the problem, and what we need to find. Okay, so I just start with my problem and kind of start listing what I have. So this 1 liter of gas at STP, is this going to be our initial or our final? Initial, okay? So 1 liter is going to be what variable? V1, good. Okay, so I'm going to go ahead and just label V1 equals 1 liter. And I'm going to kind of start making a list of what I have. Okay, STP tells us what two conditions?
The pressure and the temperature.
Okay, it tells us the pressure. So what's our P1 at STP?
0 Celsius.
No.
1 ATM.
1 ATM, good, 1 atmosphere. All right, and our temperature at STP is what? In Kelvin. 273, exactly. Okay, so does everyone understand where these numbers come from? This is STP, that's a specific condition. It doesn't change.
Why can't we do 0 Celsius?
Because we want all of our temperatures to be in Kelvin. Okay, so after we've got those, what does the 473 milliliters tell us? What variable would that be? V2. Okay, it's a volume, and it's after. Okay, it's after whatever change has happened. So our V2 is 473 milliliters, which we need to get to liters somehow. How can we do that? Okay, yep, we just said we divide by 1,000 or we move the decimal place 3 to the left. So that means our V2 is 0.473 liters. What are we solving for here? What variable?
P2.
P2. Okay, so do we have any change here in our temperature? Does it have any kind of information about our temperature at all? No. That means it's staying constant, so we don't really have to worry about it. It's not changing. There's nothing that's dependent upon that temperature change. Plus, in Boyles Law, we don't have anywhere to plug it in, so we don't need it. Okay? We're going to take our Boyles Law equation, P1V1 equals P2V2, and start plugging in what we have here from our list. Okay, so this whole list was to make it easy to plug into this equation and try not to get confused with our variables. So P1 is 1 atmosphere. V1 is 1 liter. P2 is what we're solving for, and V2 is 0.473 liters. All right, the whole left side of our equation is just going to be 1 times 1. So 1 equals 0.473 times P2. To solve for P2, all we need to do is divide over the 0.473.
2.1.
What did we get for our P2? 2.1, and our units should be?
18.
Yep.
Yeah.
Yep, pressure, so we want it to be in atmospheres. Okay, it especially has to match our original pressure unit. Okay? So since our volume did our volume expand or did our volume compress? Compress. Okay, got smaller. See, I'm using your vocab words? Yeah, okay. So our volume compressed, which means what should theoretically happen to the pressure? If they're inversely related, it should go up. And did it do that? Yes, it did. Okay, nailed it. Okay, so go ahead and do this problem on your own. It's the same type of setup, same everything. It's a little easier. You don't even have to convert anything. People that are finished? Yes, we agree?
Yes.
What happened to the volume here? Expand or compress? Compress, so the pressure should have gone up, just like the last problem. Okay, if volume goes down, pressure goes up, which is exactly what happened. Okay, so what questions do we have about where these numbers got plugged in? Anything? Pretty straightforward, right? All right, let's try one more Boyles Law.
Hey, special real quick.
All right, so this here, 835 milliliters, tells us we need to convert that to liters. Okay, and I went ahead and did that. We divided by 1,000 or moved it 3 to the left. That gives us 0.835 liters. This millimeters of mercury, what variable will that be for? Which one? P1. But can we keep it in millimeters of mercury? No, we want it in atmospheres. So how do we convert from millimeters of mercury to atmospheres? We're going to do a really, really simple T-chart. So 782 millimeters of mercury. We want to get rid of millimeters of mercury and go to atmospheres. Do we have a conversion factor to go from atmospheres to millimeters of mercury? Yep, 1 atmosphere equals 760 millimeters of mercury. So there's our conversion factor. So essentially all we're doing here is taking 782 and dividing it by 760. Okay, are we clear on that? That'll give us about 1.03. So to find our volume 2, we're going to take 0.835 liters plus 0.424 liters that I added to it. And that should give us, I think, about 1.26. And we're going to solve now for P2. Isaiah, what'd you get?
0.68.
P2 equals 0.68. What's our units? ATM, or atmospheres. All right, Charles' law tells us that the volume and temperature of a gas are directly related. So when we say directly related, we mean that when one goes up, so does the other. Okay, so here you see as the graph increases, so as we get an increase in volume, we also get an increase in temperature. So this is our directly proportional graph for volume and temperature.
So if one goes down, the other one goes down.
Yep. If one goes down, so does temperature. Okay, if volume goes down, so does temperature. Those two are directly proportional, or related, I guess. We can compare them using this equation. V1 over T1 equals V2 over T2. The 1 and the 2 mean the same thing here, so 1 is going to be our starting side or our initial side. This will be our final side or our ending side. So this is before the change happens, after the change happens. This says I have 67 liters of helium in a balloon at 28 degrees Celsius, and I increase the temperature to 47 degrees Celsius. What will the final volume of the balloon be? Okay, so get written down what you need to. Start making your list. I'll give you a couple minutes to get it written down, and then we'll start with the math. All right, so our 67 liters tells us what variable? Yep, V1, volume 1. This 28 degrees Celsius is going to be our initial temperature or our final temperature? Or T1 or T2? T1. So can we keep it in Celsius? No. So we need to take 28 plus 273, which will give us, I think, 301. And is it degrees Kelvin or just Kelvin? Just Kelvin. No degrees sign for Kelvin. We're going to solve for V2 because we want to know final volume. And we know our T2 is 47 degrees Celsius. So we're going to add 273 to that. And we get what? 320, I think? 320 Kelvin. All right. So now we have 3 of our 4 variables that we need. We can go ahead and start plugging into our Charles Law equation. V1 over T1 equals V2 over T2. Okay, so we're going to take 67 liters over 301 equals V2 over 320. Okay, so how can we solve for this V2? Cross multiply and divide. Okay, so cross multiply and divide. And that should give us a volume for V2. What'd you get, Autumn?
71.23 liters.
Do we agree? What happened to our temperature? Did it go up or down? Up. And since we know volume and temperature are directly related, what should happen to our volume? It should go up, which it did. Try this Charles Law problem on your own. 130 liters of gas at a temperature of 250 degrees Celsius. If I compress the gas until the volume decreases to 85 liters, what will the temperature be? So here you're solving for T2 instead of V2. Do we agree with this? 342 Kelvin? Shake your head yes if you agree. No if you don't agree. Okay, now what if I wanted the answer in Celsius? Tell me the answer in Celsius. Sorry. How hot will a 2,300 milliliter balloon have to get to expand to a volume of 4,000 milliliters? Assume that the initial temperature is 25 degrees Celsius. So we want to find how hot, which means we're solving for T2. What do we need to do to both of these volumes? Yeah. Divide by 1,000 or convert to liters. All right, Anna, what do you think? What'd you get for T2?
513.3.
And our units are? Kelvin. Good. Yes? No? I agree.
I agree.
Okay, what questions do we have? So pressure and temperature's relationship is also directly related. So if we want to look at our little graph like we did for volume and temperature, it would look like this. Okay, so this would be temperature, this would be pressure. They're directly related. So as one increases, so does the other. Okay, as one goes down, the other one goes down. That's what directly related means, or directly proportional. Uh-huh. Yep. So our equation looks similar also. So now it's going to be P1 over T1 equals P2 over T2. This is the least common of the gas laws. For some reason, this one just doesn't get used like the other ones do. But we have it. Okay. So P1 over T1 equals P2 over T2. One goes up, the other goes up. That's as long as you have constant volume. Okay? If you don't have constant of whatever is left out of your equation, then it doesn't work. So like in our Charles law, if we don't have constant pressure, it doesn't work. Okay? It won't have a directly proportional relationship. All right, so let's try this one quickly for Guy-Lussac's. Determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 degrees Celsius to 30 degrees Celsius. All right, we want to find the pressure change. So that means we need to solve for P1 or P2? P2. Good, P2. Okay, so constant volume means that we are able to use this equation. 1 atmosphere is going to be our P1. This would be our T1 and T2, but we need to convert those into the correct units. Claire, what'd you get? Good. We agree? Yeah. All right, perfect. So now let's look at the combined gas law. What we're doing is putting all 3 of those together. Can anyone take a guess maybe what it would look like? Anyone have just like a little guess?
Oh, we should try to guess it.
No, we're not going to not guessing the name. Try to guess what the formula would look like. Anyone have an idea? Okay, let's go ahead and take a look at all 3 of our laws, okay? So our first law was P1 times V1 equals P2 times V2. Our second law was V1 over T1 equals V2 over T2. Our third law was P1 over T1 equals P2 over T2. All right, Caleb, tell me what you think.
P1 V1 over T1 equals P2 V2 over T2.
Perfect. Okay, so all we did is take these 3 laws and we're going to combine them into one. I'll give you a little bit better description of that. Okay, so all we're doing is taking these 3 laws and literally just smushing them together into one. So we can look at all 3 of those components in one equation. So let's start working through our list here. It says this child has a toy balloon with a volume of 1.8 liters. So that means 1.8 liters is going to be what variable for us? V1. Good. 1.8 liters. The temperature of the balloon was 20 degrees Celsius. That's going to give us what variable? T1, which means 20 plus 273, yes, is 293 Kelvin. Okay? Pressure was 1.00 atmospheres, so P1 equals 1 atmosphere. Okay, we're already halfway through the word problem. Is this so difficult? No. No, it's not.
They're only difficult. I'm crying on the inside.
Okay, V2. What do we have? Do we know what V2 is? No, that's what we're solving for, so that gets our question mark. Okay. Up here it tells us the pressure is 0.667. What variable goes with that?
P2.
Good, P2. And finally, what's this negative 10 degrees Celsius going to be?
263 Kelvin.
Good. T2, that's our final temperature, is going to be 263 Kelvin. So even though we had a negative degree Celsius, we're still going to add 273 to that. What about the 3 meters? Do we care about that? No, we don't care. Okay. Let's go ahead and start plugging into our equation. P1 V1 over T1 equals P2 V2 over T2. All right. So we'll plug in 1 atmosphere times 1.8 liters over 293 equals 0.667 times V2 over 263. Okay, so how do we go about solving this particular equation? We can cross multiply and divide. It might be a little simpler to just solve this whole term first, and then you can cross this 263 up, divide by the 6.667. Okay, so solve this whole term, then you can multiply this 263 up, and you'll divide this 0.667 down. Okay, so we'll solve for V2, and tell me what we get. Units. Try this one on your own. We do have to do a conversion here. 1825 millimeters of mercury. You need to convert this volume to liters. You should know how to do all those things. Do you guys agree with what I had up on the board? This number right here? I don't. I don't. I thought I changed it, but I didn't. Okay, so it should be like 242. Okay, that's what I thought. I changed everything else I was supposed to change, but I didn't change this. Okay, so we got about 242 something Kelvin.